Is it a bird?
Is it a plane?
No, it's 1,000 hour aviation. Today we're going to be doing some calculations to try and figure out how we're going to build a plane for our EPQ. So for the plane for plane to take off, we need to go. We need speed. Plane. We're going to need some forwards thrust.
Kinetic energy.
Yeah, kinetic energy, and we're going to get that from some motor, maybe an engine or a
We could use some diesel, or we could use a battery.
yeah. We could have an electric motor or a petrol motor.
We could
Um,
also use some helium to lower the weight. Not
yeah,
lower the weight,
that's later. We
increase the
also
buoyancy.
we need to go forwards and then have some wing, and then the wing gonna like generate lift. We make lift,
I'm not watching the stream.
and the lift has got to be greater than the weight by gravity. The weight.
You got
And
drag.
we're gonna have some drag, and we don't know how big the drag's gonna be.
It's got a bit of friction, normal contact force.
No, we're in the air.
Ah, okay, in the foot. Yeah, all right.
We're in the air. So this is
Mm.
this is what we need to do. And to do this, we're going to like it's not working. We're gonna make a plane shape with some wings. We're gonna make it pretty light. I don't know how light. Be the wing, so we're gonna have it like this sort of shape ish. Something like
So make
this.
a cross.
Yeah, kind of like something that's a cross. And then we're gonna have a like propeller on the front and some like tail on the back. The wing shape, we'll probably just make something that looks wing shaped.
We could make the
And
wings out like styrofoam to lower the weight.
we'll make it all out of styrofoam. Because sadly we're not gonna be getting in this anymore. Because we can't get the budget to make a big plane like we were intended to. So we're gonna have to make an RC plane. So you can make it big. So if this plane here weighs 1 kilogram, then we are gonna, with all the parts, then we're gonna need to times that by gravity. And that's gonna get us 9.8
What about the height?
newtons.
Oh, is that the weight?
Yeah.
Right, okay.
Is that it? It's a lot lighter than I expected. And then,
I have a feeling it's going to weigh a bit more than 1 kilogram.
but that's what we're hoping for. 1 kilogram is what we're hoping for. It's going to weigh. And then we need to lift 9.81 newtons off the floor. So our wings, these guys, these guys need to produce 9.81 newtons of thrust upwards. And to do that,
An arrow.
yeah, up thrust in the upwards
And
direction.
it'd be going like
It should really be going
towards.
out. It should really be going out of the page, but I'm not going to draw on that. So
Right.
yeah, go.
Right.
So the equation that we're going to use to make it go to make calculate our up thrust. So we need 9.81 newtons, and we need to figure out how fast we want to go to get 9.81 newtons. Yeah. So what's the equation?
So the equation for lift is lift equals coefficient times density times velocity squared over 2 divided by wing
Hang
area.
on. Times density
You want the symbol equation first?
times what?
You forgot the coefficient where lift equals.
Oh, equals. Hold up. Equals. Yep.
And you forgot coefficient in the middle of that.
The coefficient go after, yeah?
Times velocity squared.
Co.
And for some
Fish.
reason, the density and the velocity squared are only those two are divided by 2 for some reason, even though it doesn't matter when you multiply them all. Times by wing area.
Velocity squared times wing area.
You know that's
Yeah.
all illegible. Times by
Wait,
coefficient.
we got coefficient over here.
Oh, okay, over 2.
Over 2.
Mm-hmm.
So we
And the
know,
coefficient
yeah.
contains all the complex dependencies and is usually determined experiment. I can't say that. Experimentally.
And what number do we have?
Number what?
The coefficient
Oh,
number.
I don't know. We'll figure that out later. You want the word like the symbol equation so we can
Is there like a delete all button? Oh, I'm doing pressing buttons I shouldn't be. Ah, fixed it.
I think that's fixed.
Yeah, it is. It is. I'm fixing it. Don't you worry. How how do we use fixed it?
There we go.
Okay, so we need
Right.
9.81 lift. So we've got to equal 9.881.
Not, so L equals CL, which is the coefficient.
What is the coefficient? I need a number.
We'll get that later. Just put CL for now.
Okay, coefficient
Worst,
of lift.
worst case, we'll just use like the atomic number of chlorine because Cl and chlorine,
Alright, yeah.
times
Okay.
by P. Though I think that's a rho because rho
Yeah,
don't have enough users
density.
yet.
Density. Yep, density.
Times by velocity squared.
V squared. 2s?
Times by wing area.
Is that not like
A.
we
Area. A.
A W
Over 2.
over 2.
Mm.
So it's 19.62 equals that lot. And what's the so
What
what do
velocity
we
are we going for?
I don't know. We need to do a bit more research for that. So to calculate how fast we're gonna have to go, we're gonna have to figure out everything else. So the area of the wings, we can do that. So we're gonna have a 40 centimeter wing on one side, and it's gonna like in length, and it's gonna be 10 centimeters deep, and we're gonna
SI
have two of
unit.
them. Yeah, we're in centimeters, which means we need to like
Oh, it's going to be
we need to divide this.
0.08.
Yeah, 0.08. 0.08 meters squared. And the density of air, we need to figure that one out. And the
Out air.
coefficient of lift. For a general, wherever it is, for a general wing at a 10% angle of attack. So that if the ground is horizontal at 0, and so the nose of the aircraft is pointing up 10 degrees from the floor, then the coefficient of lift should be about 1.5. So we times that by 1.5. It isn't in the correct order, but yeah. And now we just need to find out what the density of air is in England. You know what the density of air is in England?
Hey Google, what's the density of air in England?
Metric units. 1.225 kilograms per cubic meter.
Do you get that?
Density? No, I didn't hear that. What's the density?
1.225 kilograms per meter cubed.
1.2.
That's at sea level, at 15 degrees atmospheric pressure.
That'll do. 1.225 times v squared.
Do you want it in pounds per feet?
No. So now we just need to divide that by this bit and square root it.
Let me just like do in my head real quick.
Can you put that in your calculator, please?
Yeah, I'll go find one.
Alright.
Calculator has been acquired. Fancy smancy pink calculator.
What's the pink one?
19.62 divided by 0.08 times by 1.5 times 1.225 comes out to 133.496, but I have to square root that. Square root odds. So that no, I haven't square rooted. Square rooted, it's 11.553. Actually, do you want all the decimal places?
0.5
55289.
Was it 2 2s?
No, 1 2. 8 9
9
5 2 1.
2 1 meters per second. So that means that our plane only has to go about Usain Bolt speed.
A bit faster, I think.
Yeah, slightly faster than Usain Bolt. We gotta go when he ran his 100-meter world record. That should be pretty doable.
I reckon I can throw that fast.
You're gonna throw it, but it's not gonna have permanent lift, is it?
Yeah, true. My angle of attack would be like -5.
So to go at 11.5528951 meters per second, we're gonna need some form of engine or motor to actually to convert some energy store into kinetic energy. So we have found on here this website, Sunny Sky USA, for only the low price of £10, this A2212 brushless motor, which, if we scroll down here, if we run it at 12.5 volts and a current for it of 9 amps, then it produces a gram force of 700, which in this converter is 6.8644655 newtons. So like 6.86. And we want to make our plane weigh 1 kilogram. So if F equals ma, that means that A equals our force divided by our mass. So 6.865. I'm right, 6. 5 divided by 1, which equals 6.865 meters per second squared. And so we have learnt that air resistance is negligible at low velocities, which helps us here because we can now use Suvat equations to help us with figuring out what we're gonna do. So I cannot exactly remember what. Can you remember what the velocity? Don't worry, I took a screenshot. It's all good.
Which one?
So we want S U. That looks like a V. Very bad. U V A T. Okay. So, and we want to work out How long is so? This obviously will be 0 meters per second. Our final velocity will need to be like 11.6. We'll round it
It
up.
was.
It was
Wait, hold on.
5. It was 5.528.
11.553.
Yeah,
Yes,
but that's
11.6
well.
works.
We'll round that up. Meters per second. We'll go a bit faster.
If
I
it's
don't
a
know why I
bit
wrote
faster,
I
it's
don't know
gonna
why I
be
wrote meters
okay.
per meter, but that's
Meters
alright.
per meter.
And our acceleration was 6.85. We'll round it down. We'll round the acceleration down. And the time, we're going to work that one out. How long will it take us to reach that? Because if it's some ridiculous number, like 5 million seconds, then we're not going to actually reach the velocity that we need. So,
So we want the
okay. So what equation are we going to need to use? Um,
V equals UT.
plus half AT squared.
No. Wait, hold on.
It is. It is. V equals
equals
U
UT
plus
plus
half
A.
AT. V equals U plus AT. Yeah,
Yeah, that one. V equals U plus AT.
because the other one, it's S equals
Yeah.
UT plus half AT squared. U plus AT, yeah?
Yeah.
So we got 11.6 equals 0 plus 6.85 T, which means that T
Is
equals
1.69.
11.6 over 6.85. Yeah, that's a mess. Which equals what?
1.69.
1.69. Nice seconds. Which means that it's a reasonable amount of time we could do that. However, we are planning on using 2 of these brushless motors because we want to make a VTOL aircraft. Yeah, so we're trying to build a VTOL, which is something like this. The V-22 Osprey, which, as you see here, it's got its propellers facing upwards. It's got the wings in the middle. But then it can transition to forwards flight, where there was a picture here, and I've lost it.
To the right.
Over here, where it can have its propellers facing forwards, which is more efficient because it's not having to use it's not having to convert its stored energy in probably like jet fuel. It's not going to have to convert that into the kinetic energy for the upthrust to oppose its weight. It can use the oncoming air, which is normally oncoming anyway, to go flow around its wings to get a pressure differential where it's got low pressure above and high pressure below, which effectively sucks the aircraft upwards, which requires less energy than if its propellers were vertical like this. And that means we're going to have 2 motors.
You also see
So,
the guy with almost falling out the window.
if we have 2 motors, our time, in theory, should be
Half.
halved.
Or
However,
0.85 seconds.
this means that the aircraft will have to have its propellers completely flat because these stats on here are with the motor that way, with the propeller on this bit, and it's traveling left to right on the screen, that direction. But ours will be vertical, a bit like this, or slightly tilted forwards, about like 45-ish degrees. So our actual forwards acceleration won't be that great. It will be something, and it'll be
Right, okay.
so if we if we're gonna have the
Okay.
motors tilted about 45 degrees to try and allow us to get up and forwards at the same time, this means that we will need to be able to transition to forward flight. It won't actually take us 8.5 seconds. It should be our acceleration is actually 6.85 cos 45 degrees. What is that?
That's half 0.5 times 6.85. That's a syntax error.
Because if
it is 3.425.
Which, when you think about it, because cos 45 is a half, that means that is halved. Our acceleration.
Can I correct myself? Cos 45 is not a half. That's cos 60.
It's not a half. Well,
It's a root
Jacob
2.
here is doing awful. So what's the actual answer, please? That it actually is. So we can't just
6.85.
You don't use
It's
a
actually
calculator.
4.84.
So if we just correct this value up here, we'll just cross that out. Divide by 4.84. What is that? Got this. Cross up this too. This is wrong. That's wrong. All of it's wrong. Well, it's correct if we're going completely forwards, but we want to vertically take off and then transition.
Is that 4.84? That's the vertical.
Vertical is horizontal. 11.86 divided by 4.84. So we need to work out. Is this too much complex maths for you, Jacob?
Wait, what were the numbers?
11.6 divided by 4.84.
4.84. Yeah. It is 2.39669.
Which means we can half that.
By 2?
By 2, which equals like
1.198.
1.198 seconds. Hopefully. If we hope that that's enough. So in theory, it is doable with 2 of these motors. And then we can just have them on a pivot and some other servo motors or something like that to make them tilt up and down. And then we'll just have like a big bar in the middle with some wing attached to make the aircraft. And then we can have like some wheels on the bottom. We don't really even need wheels because we're not going to travel anywhere by like ground. So in theory, this should be doable. So we have proved that it is doable to actually make our VTOL take off, hopefully, and go forwards flight and then transition back to vertical and then land. So thank you for watching. I hope you enjoyed our amazing calculations to calculate that we need these motors, wherever they are, and that we need to travel at like 1.19 seconds to again make us got 11.6 meters per second. Then we can transition to forward flight and keep going.
Yeah.
Bye.
See you next time
On 1,000 Hour Aviation.